Okay, so here's the agenda for today's session. We're going to start off with an introduction to what HPMS is and why it presents specific challenges or unique challenges to transportation reporting. We'll talk about the HPMS preparation process in general terms, what that looks like, and how we took those requirements and built a product called the Transportation Intelligence Gateway around them. We built this product called the TIG for short to satisfy HPMS requirements as well as most other complex reporting requirements, transportation reporting requirements. After I describe what the TIG is, we'll go ahead and talk a little bit about what the future holds for TIG and what the future holds for HPMS. I am on the committee that's doing the HPMS reassessment for version 9. We have a series of recommendations that were formulated. None of them are final yet. They're all recommendations, but I'd love to hear your feedback on them. So we'll go through those. And again, for those of you who know HPMS, know TIG, or know Tom Roth at the FHWA, you know that each of these topics could occupy several hours worth of discussion. So we'll try to fly through at a high level. But if you have questions, please let me know. It is, of course, a challenge to talk about things like HPMS, which is quite complex, only at a high level. The magic of the applications the application that we developed really occurs at the technical level, and I'm always happy to show that off. And again, I think the tool is positioned strategically and tactically to help with HPMS and a whole bunch of other reporting requirements. So specifically, what we're going to do is talk about several components of HPMS, not all of them. It is a universe unto itself. The HPMS system was developed quite a few years ago, 20 years ago, by the FHWA, and it's the process of collecting data from each of the states through apportioned federal highway funds and basically for strategic planning and performance reporting. And so there are several pieces of legislation that authorize the federal government to collect this data. And again, Title 23 is the big piece of legislation there. And so HPMS, as a series of collected data, is organized into catalogs. And so I've shown 3 of them here. The shapes catalog, which is essentially the FHWA asking you for a copy of all of the shapes and a small number of attributes of the route system that you report your transportation data against. And they take that shape, that series of shapes, one for each route, and they compile at the federal level a national map of the U.S. Transportation system. They lay on top of that map all the rest of the data that they collect, including summary data. For example, a county summary data. There are 6 or 7 different summaries extracts. The one I've listed here is the county data, which is essentially pavement information, road mileage that's aggregated to the county level. Also in the sections catalog, a third catalog, you have a list of sample panels and sections data. And that consists of 69 different measures of your transportation network that are broken into the categories of inventory, route, traffic, geometric, like curves and grades, pavement, and then special networks. So those 69 data items are all aggregated into a sections extract, which is part of the sections catalog. The sample panels are areas of your network that you must report against for federal reporting purposes, for HPMS purposes. And what the sample panels essentially are is a listing of the locations of where you're doing that specific measurements, those specific measurements. Okay, so what we have here, just in this slide, are 4 different extracts that we can satisfy with one application. And you can probably get a sense of the difficulty or the complexity that has to exist in this application in order to satisfy such disparate types of extracts from spatial data to summarized data to very detailed data as well. Okay. All right. So generally speaking, when you prepare HPMS, you have the preparations in this blue box. You're relying on your DOT asset management system and your LRS system. And in this system, you take ownership of field collected data. If you're using alternative data sources, that as well. You store, maintain, and then report against your state data here. And then in the HPMS data preparation process, you perform sums, min, maxes, averages. You do length-weighted averages and predominance. You do some combination of things like stop signs and turn lanes. And then you do codes and decodes, like for curves and grades. And then you must, in some cases, probably apply some specific functions for it. So there's a whole series of activities that one engages in to prepare the HPMS data for submittal to the FHWA. And now this process for most states is quite a large undertaking. But as you can see in this diagram, the complexity although the complexity is isolated here in this blue box, this is not really representative of what a typical DOT looks like data organization-wise. This is a little more typical, where you have data spread throughout, you have different owners, you have different combinations of collections of data, and it's this morass of data that you then have to send off to HPMS for your analysis. So the difficulty, I call this the distributed model, where you have all sorts of data silos. You have an LRS, some people have an LRS system, some states have an LRS system separate from their asset management, separate from the pavement management, separate from their signal database, separate from the local road database. And in order to produce HPMS, you have to combine all these things. So when we say taking the complexity out of HPMS, the TIG application had to develop a mechanism or a means of simplifying this data aggregation or this data collection process. So here we can see in this diagram basically that there are multiple data silos with multiple owners. These could perhaps be the data stored in multiple linear referencing methods. We have pavement, which might be every 10 feet captured XY, whereas signs you might have by route offset. Could involve multiple technologies. Oftentimes is the case, we have sole experts who know how to collect it and manage all this data, and then they retire or they win the lottery and then they're gone. The systems here are typically inflexible. This whole process of collecting the data for HPMS can oftentimes be quite costly, and it's difficult to systematize. All right, and by systematize, I mean push a button and have it all work. All right. So based on that as the backdrop, as the scenario, how do we take the complexity out? So what we did is we worked with the state of Oregon, and we designed the Transportation Intelligence Gateway. So this wasn't a creation by essentially developers sitting in a back room pondering how to make this easy. This is Bentley working with the marketplace and asking them, what's going to make your life easier? And so again, market-based design. So we need to be able to access data from multiple sources. So that was a requirement that was built in. We need to accommodate multiple linear referencing methods, remove dependencies on custom programming. In other words, build in all those functions which HPMS requires, like predominance or like rolling up to a county. Build that in so you can select those things via a menu as opposed to having your development team build that. It has to automatically be able to chop up the network into like chunks called dime figging, and it has to be able to do so in a manner that's menu-driven, easy to use. We need to apply any of the aggregate, analytic, or custom functions that our accounts have developed. Has to be spatially enabled. Route shapes requires a shapefile. That has to be a natural output of this application. And again, we need to be able to roll up data along a route so that if you have chopped up your network based on 4 or 5 criteria, you can glue it back together if you're only looking at 2 of those at a time. We can roll up data along any criteria for the summaries catalog and estimates catalog as well. It has to be an application that's secure and fully documented, which again would protect you from updates. And again, we wanted to build this in a manner that was more than just for the use in HPMS. In fact, we have some non-US accounts on this call right now, and we actually are using this application in Canada, India, Australia, and all around the world. All right, so the TIG, this is the login form. As you can see, this yellow background box is just a bit of a blurb about what you can do in the application. This is the organization of the data here. So if you notice, we have extracts. This extract FS_QC, it's a functional system quality control extract, is placed in a catalog. So we have organized the extract definitions by catalog in a manner very similar to HPMS. You can also see who's logged on here. So it is a secure system. You have to have the correct right in order to access this. All right. All right. So in general terms, in the abstract, at the highest level, we have this tool here. And what you do with this tool, the TIG, is you build an extract definition. And there's a bunch of things you can do in that definition. In that definition, we've built this, what we call the abstraction layer, that allows you to pull into this process any linear referencing data or any of your asset data. Now, by default, it will automatically have awareness of everything stored in the Bentley system. But the application is not limited to Bentley. In fact, we have some accounts that use this on top of a data warehouse, not on top of XOR software. So you have your choice. So again, we have an extract definition, and I'll talk to you about what that means. And we produce some output. There are intermediary steps, and I list here views and procedures because what this extract definition does is it presents the user with a bunch of user interface options and menu options that through which the user will configure what they want out of the system. The system then goes ahead and translates that or compiles that into a bunch of views and procedures, which are all hidden from the user. So you don't have to worry about how to optimize queries or how to do joins to various tables. The system handles all that. So that's all hidden behind the scenes. So what the user sees is this extract definition, and they see the output. The output can be either a map, an attributed map, or it can be an attribution table. And again, the Transportation Intelligence Gateway, because it has this abstraction layer, can then look at that data as if it were yet another asset. So again, we'll get into this in a bit. So in this extract definition, you can say, what's the state of my network today? Save that as an output. And then a year from now, what's my network status today? And then compare last year's to this year's to produce what changed over period end to end one. So you can do all sorts of neat things with the system's ability to actually look at data it's produced itself. So this is an extract definition. Here we descend into the weeds, and I will try to not do this for too long. But an extract definition is basically made up of 4 parts. Give it a name. Give your extract a name. What root system do you want to report your results against? What do you want to collect? This is your attributes to collection and report against. Do you want to map? Yes or no? So those are the four bits of an extract definition. All right. And what this extract definition does is it assembles, aggregates, and analyzes your transportation data. All right. What data? Well, whatever data you choose. All right. So the data is extracted through this process. And it can be, like I said, the output of this can be used as input to another extract. Okay, and so let me go give you an example. So root shapes. We're all familiar with root shapes. It's one of the simplest HPMS requirements. This is what the root shapes extract would look like. Summary information. I'm going to call it HPMS root shapes, just giving it a name. There's some other summary information that you can provide, like what is the table name of the data that you're extracting out? Where are you going to store the shape data and the attribute data? That's also listed in the summary information. But primarily, it's what's the name of the extract? What information do you want out of here? Against what root system are you going to report? Well, this is root shape, so I want my state root system. All right, and well, what do you want from that state root system? Well, I want to know the root name and the root type. All right, do you want spatial information? Well, yes, that's the whole point. And so that's what root shapes looks like. That would, it's an extract that would take just a matter of minutes. All right. Here's another one. This is the submit sections. This is not the entire submit sections, you can tell. What are you going to call it? I'm going to call it HPMS submit sections. Against the state root system, I want to collect all these things. All right, so an attribute set, the first one, attribute set number one, is called F underscore system. And in there, I want to extract out the code and the text. So I create an attribute set that does F system. I create another attribute set that includes my urban and rural codes. All right, I'm including these in the output table. I do some counting of stop signs. I'm not going to include this attribute set in the output, but I'm going to create an attribute set to take advantage of all the aggregate functions and all the analytic functions to do some mathematics on some raw data that I have. And I don't want to include all that raw data in the output. I want to use the summary of it. So I have an attribute set that goes ahead and does all those formulas and all those aggregations and analytics, summarizes it, and then in a subsequent attribute set like turn lanes, I can use the stop sign count, all right, along with my left turn lane data. Okay, so this attribute set collection, you can have any number of attribute sets in an extract, and in fact, in most of our states that use this for HPMS, they have over 100 attribute sets, 69 of which are included in the output. The rest are just these types of things where you're using them for calculations. Okay, and spatial information for sections, there is no spatial information. The FHWA is only interested in the attribution. All right, so again, what we're talking about is this menu-driven analytics capability here. So what I've just shown you fits in this box. And the reason we're able to pull this data together is because we have pointers to all the different asset data in linear referencing data in that level, in that layer of abstraction that I had pointed to earlier. So the reason I'm going to just turn back one slide. So functional system, urban code, the sign database, turn lane database, all those could be in various systems spread throughout your organization. We've just gone through a process of making them aware to TIG. So now you can use them as if they're all in the same system. The TIG doesn't care at that point, so long as you've identified where they're located. And then you can do analytics based on any comparison to any of that data in that collection. And the output of which, of course, are your BAPs or your logical data or both. So this is for the location information. So in both the root shapes and in the submit sections, this is what you would say for the location information. Remember, I said there were 4 parts to an extract. One is the summary information, which is just giving it a name and giving an output table and a few other things, which I'll show you in a moment. Then specifying against what root system you're going to report your results. We're going to report our results against the state root system. All right, I believe this is Connecticut's system here. And so when you select, I'm going to report against the state root system, it automatically fills in all the green fields. And for HPMS purposes, we've added the state code, the section length, and the year of the record. Section length is a formula. The reason it's a formula is because, again, if you're looking at a number of different assets that you're pulling together, the system will dynamically segment your network based on the attribution of those assets. And so the section length is calculated based on that dynamic segmentation. So if you remove some assets from consideration, the section length will change accordingly. The dynamic segmentation is truly dynamic, and therefore the calculation of the section length also has. In this case, we're looking at all state roots. For the purposes of producing an HPMS extract, typically you would limit it, say really only where the root ID is equal to root 1 or something. Just you run it against a root, and then you remove that constraint and let it fly across the whole network when you're ready. All right, so for F system, so here we have the step 3 information. This is an attribute set. An attribute set, as you can see, this attribute set has 3 rows in it. The first, I've taken a text value called F underscore system. That's my data item. All right, and if you're familiar with the submit sections extract in the sections catalog, you know that one of the required output columns is called data item. The functional class code, I'm taking out of my functional class asset, just taking its value. and I'm putting that in value numeric. And what I'm also going to do is I'm going to decode that or take that code and turn it into a description and stick that description in value comments. Now, I didn't have to type in this formula. That's an automatic. When you say formula, yes, you can automatically generate that formula. So again, we've tried to take the coding out of this as much as possible. And as you can see, I haven't restricted the data at all. So this will work for the entire root system that I've selected. Okay, if you want to count stop signs across the sample panel, this is how you do it. As you can see, it doesn't get easier than this. I'm going to count. I'm going to look into the sign panels for each unique ID. I'm going to count them. All right, and I'm going to count them within a range of a sample, an HPMS sample. And so that's how easy it is. There is no coding. There is no developer required here. And actually, I'm going to limit that to just stop signs. Now, there are you would think that this would be a relatively simple thing behind the scenes, and you would be wrong, because what happens if you have two sample sections that abut one another, and there's a stop sign that separates the two. That stop sign is technically in both, but you don't want to double count it. And so we have code behind the scenes that resolves that. And it takes the lowest mileage sample section and puts the shared stop sign in that one. And so again, that's the voice of experience speaking, and that's the direction we receive from our accounts, like Oregon, who deal with this problem or dealt with that problem prior to this. All right, so just in general, then the generic capabilities, those actions that I showed you here. I've showed you count, range, value, and text. Well, here's the whole list. You can take the value out of an asset. You can create a text field that you want in your output, or supply a function. Or you can do a sum, a count, a min, a max, an average, a length-weighted average, or a most common value over a range. So these are the functions that the system will perform automatically, in addition to any other function that you have already developed. You can stick that in a formula box here. So you have a formula, yes or no. If you say yes, you get an editor form that allows you to put in anything. All right, so you can see here the asset or group ID. This was from the sign panels. This is a list of all of the assets that the system that have been identified to the system. As you can see from the elevator bar here, they have over 200 different assets. They being Connecticut in this case. 200. Actually, I think it's more like 100 and some odd different assets that have identified to the system, listed alphabetically. The blue items here are point items. The black ones are linear. And so when you select an asset, then you get all the attribution at your disposal as well. And so I can take all of the attributes of sign panels, or in this case, I'm only interested in the assembly ID. You can include this. In this case, it would be the value from the sign panel asset of the assembly ID. I can include that in the output, or I can not include that in the output and just use that as a calculation within this attribute set. And then I can add a formula. The output column, completely flexible. You can change that to whatever you'd like. So just again, a generic case, if I wanted to show the speed limit, functional class code, the town name, and the county name for Hartford, Middlesex counties, you just pick them off a list. And I put the where clause in here, Hartford, Middlesex. What this is going to do is dynamically segment your data based on all those. You can then roll that data up so that like rows are joined in one segment. Okay, so there, again, this is very fast. It doesn't require custom programming at all. It creates spatial data. You click on a field. These fields fill out automatically. All right, so the options here, you don't need to have spatial output in your data. You can if you want. It'll be based on root mile point, or it'll be based on the topological network on which this root mile point sits. And so you have a choice of either using the LRS that you've selected in step 2, or the topology that underlies it. You also have the option, if you're a superload account, to create the linear attribute and linear coordinate file. The linear attribute file is generated through the rest of the extract. This spatial data is a linear coordinate file, and you'll get 2 outputs from this if you're a superload account. Okay, so incorporating data that's not resident in an Expo system, you can simply just, this is a form here. You can see not a lot of information is required. You give it a name, you give it a location, and you tell the system how the data is located. Is it root mile point? Is it topologically connected? Does it share a common attribute with an existing asset? You could also identify here data that's stored with XY, and you can convert that from XY to a linear network as well. You can also build custom routes. Custom routes are important if you have concurrent routes and you want to report against only those that are primary. In other words, you have Route 4 and Route 225 that lay across the same road. Well, for reporting purposes, you only want to report against Route 4, except for that section where Route 2 overlays both of them. And so you come up with custom rules that say take the lowest numbered route, highest functional class, order them ascending. So you can do that on the fly, so you don't have to have that data stored in your linear referencing system. That'll be a function of your reporting system. It's a very important piece of functionality there. So just to recap, the root shapes, as you saw, was a very simple extract definition. There was one attribute set where you said spatial equals yes, and you pulled out your state root system. You submit sections with 69 different attribute sets, plus any number of additional attribute sets that are used for calculations. One calculated attribute set can be used by any number of subsequent attribute sets. So if you find you need stop sign count used in 4 or 5 different other attribute sets, well, then you can just calculate it once and then go ahead and just refer to it. This submit sections is one executable. So there you have your magic button at the end of the day. After you've defined this, you have one executable that you need to execute to generate your HPMS. All right, all the data connectors and joins all handled behind the scenes. You don't have to worry about any of that complexity. In addition, you can assemble validation extracts, which basically, because again, you can use this as an input, you can create an extract that looks at this data and performs any of the validations that the FHWA requires. And if those validations change over time, which they do, you don't have to worry about having a software update like other products require. And again, the results can be either map-based, logical, or logical. All right, so some special features. I'll just go through a few of the special features. For those who use the application, you may be aware of these, you may not. One of them is this effective date processing. So we have a field right here. It says output will be generated using effective date. Oftentimes, states will shut down their network editing while their HPMS data is being performed because they don't want to corrupt the data. They don't want to have the data spanning edits. But what effective date processing allows you to do is it allows you to supply a date, say March 1st. All of the data will be extracted as if it existed on March 1st. Even if there's been substantial editing since that point, the system will roll the clock back and only look at that data. So it is time sensitive or date sensitive. You also have the ability to just run one attribute set at a time. Right here it says limit the output to include only data items. In your HPMS submit sections, you're going to have at least 69 here. And if you're having trouble left turn lanes, you can just run it. You don't have to run the entire extract. You can also order and index the columns for output as well. All right. We also have these two functions which are quite useful. One is called consolidate. So if I wanted to produce an estimate or something for the summaries catalog, I wanted the average AADT over for each town. Well, again, I just specify the range of a town, the average AADT, and I can do a consolidate. And what that consolidate will do is it'll roll the data up to the town, or to the range item to town. And so you're not getting AAT values for every route. You're getting a summary in the town. So this is used to roll data up according to any criteria that you specify here. It's of particular use in the summaries catalog. There's another field you can specify, and again, that's a reserved word intake. The other reserved word intake is max length. And what that will do, if you specify a value of max length to 0.01, it'll produce output, every row of which will be a tenth of a mile, 0.01 of a mile, or is that a hundredth of a mile? So again, if you want to produce XY data for your entire network, this is the way you do it. You do max length, and the system's going to chop your network up into little itty bitty pieces, but however big that you specify with that feature. All right. So in terms of the future, we're going to be integrating TIG with the map a lot more tightly in coming iterations. All right. The other what I'll talk about next after map integration will come first. This will come second, but it's the glitzier thing, so that's why it's here first. So this map here is the AWLRS. It's Bentley's linear referencing system, brand new, beautiful layout here. Where in step 2, where I said I wanted the state root system, what you'll be able to do is just click on the map and draw a polygon, and any roads in that polygon, that'll be your location information. Your attribute sets will be determined on whatever layers you have active at the time. So basically, you come in, you can draw a circle around the map, and it's going to say, okay, that's the area you want to report against, and those are the assets you want to report against. What do you want to do with it? All right, and then you can do, show me just a list of all the assets in that area, show me all the, summarize them into length-weighted averages or whatnot. All right, so TIG will be callable from the AWLRS. It'll be another option here. All right. And then the results of that will be added to the legend where you can turn them on or off. Now, all of this applies to one of extracts. And the reason I mention this will become clearer in just a moment. And again, the reason we're doing this is because we were asked to do so by our accounts. So we're keeping a tight communication open with our accounts for this. So another future item. This is on the docket before the map integration. It's an execution group. All right. So right now, where you have a catalog, and we have it like I had shown you earlier, the FS_QC, the functional system quality control extract, sat in a catalog. That's a development catalog. We're going to have another catalog type called the execution catalog, and what it'll contain is a list of all the extracts that you want executed, what pre-processing you want done, what post-processing you want done. Do you want the results distributed, and if so, where to? So in this pavement analysis execution group, the data is generated by executing 4 different extracts, the last of which is a summary of the previous 3, and I'm going to distribute the spatial data to various places on my network. All right, because these are the folks who are interested in seeing those results. All right, and I'm going to do that monthly. So every month, now that I've got all these built, I'm just going to put together this list of extracts to execute, and the data will be automatically distributed. Okay, so again, this is systematizing the process of data distribution. It is actually generating a system, a reliable system by which you can produce and distribute an unlimited amount of data. All right, periodically. Future of HPMS. So the next version of HPMS is going to be designed to reduce the overall burden on the states. It will hopefully simplify processing and attempt to draw a straight line between collection, storage, and reporting. These are only recommendations at this point. So although I'm being recorded, please don't forward this to Tom Roth. Actually, I'll be speaking to him in about a half an hour. So again, all of this information he's already spoken to each of the states about. We had statewide, or I should say region-wide conferences to talk about these things. And so what the feedback that was collected during those processes, of which I was a part, resulted in some of these recommendations, which is a subset of all recommendations. There are some on here I'm not listing, but these are just those that apply really to the actual generation of the extract. But first, reduce calculations, and I think this is so important. So we're getting rid of having to do things like counting stop signs, calculating the length-weighted averages or predominance. 50 states in Puerto Rico are now actually doing each of these calculations. Well, why doesn't the FHWA do it? And the states just supply the raw data. So there's a movement to that. That's what this means. That rather than supplying a count of stop signs, just dump out the stop sign data. Rather than calculating the predominance of pavement type, just tell us where the pavement type is and where the sample sections are, and the feds will calculate predominance as well as length-weighted averages. Reducing dependencies. If you look at what the calculations that are involved in right turn lane and left turn lane, um, it it occupies 9 pages of the field manual. What we're doing is we're getting rid of the dependency between identifying lane types and signal types. So basically, what we're going to be doing, and this is down here in the consolidated items, which I'll talk about in a moment, is wherever there's an opportunity for us to reduce the number of different data objects that are used to do one calculation, then we break that calculation into those atomic parts. So you're not doing all the math. Reduce code conversions, curves and grades. There's not a piece of equipment in the world that will collect grades saying this is a grade A, this is a grade B, this is a grade C. What it does is it says this is a grade or a curve, and here's the degree of curvature. So that's what you'll send, the degree of curvature. One of the difficult parts of figuring out curves and grades is you have to report where they aren't. So on a sample section, grade A is where there's no B, C, D, E, or F. And so that'll go away as well. So you're just spitting out degree of curvature, and the feds will calculate all the rest of it. And the consolidating data items. So where you're talking about shoulders, medians, through lanes, left turn lanes, right turn lanes, HOV lanes, lane widths, and all the rest of the lane items, there's going to be a lane asset. Lane type, well, is it a shoulder? Where is it across the road? You know, and the feds will reassemble all that data the way they want to assemble it for calculating complex items. You're just applying the raw data. Pavement, again, pavement, rather than having thickness rigid, thickness flexible, base type, base thickness, that's all just going to be pavement. And then the variations between these will be handled with the value numeric or value text or value comments fields. Signals, you're not going to count them. You're just going to blast them in. Signal type, number of signals, stop signs, at grade other. Those will be calculated based on the signal data. And same with route number, route signing, route qualifier, alt route name. Those will be all one item called route, and their attribution will handle separating those out. So again, these are recommendations at this point. We might get feedback from the states that say, you know, that's going to cause more work, or yeah, that's fantastic. But the goal here is really just to reduce the burden. And the reason they want to reduce the burden is because there are going to be more items added, those that relate to Meyer, for instance. And so the overall effort, we're trying to keep roughly the same and make it simpler. It also will allow you to assemble the data in ways that are more meaningful to you, rather than having to come up with these combinations, which may or may not have some value to you. All right, so basically, this is the box we're trying to make smaller. And in fact, in the ideal world, this box would not exist. Field data collected, pavement data would be sent to the feds. Or you come in, you own it, maybe you maintain it a bit, and then send it to the feds. So it's this box here, which we're trying to make smaller, and trying to simplify the process. What has the result of all of this been? The TIG application results against HPMS. Well, this is a diagram we put together with our friends in Oregon, where they used to, before TIG, spend a lot of time on assembling data from various places. They don't spend as much time on that now. What they are able to do is spend more time on analysis, all right, revising the data and getting it to the FHWA. So it's a lot more efficient, and you're basically employing your experts to do export work, not doing the rote sort of data assembly work. Again, this is in regards to TIG. The state of Oregon was able to increase the data management efficiency and regulatory compliance. Their return on investment, they calculated over $6 million, which I did not get a bonus of. But at any rate, so this is all in the PowerPoint presentation. You're welcome to read this. And again, I think the experience here set a precedent that we're working very tightly with the user community to make sure this application continues to meet reporting needs. Any questions?